Hello everyone, my name is Yilong Yang. I am a PhD student from the University of Southampton, and I'm going to present rotation scale equivariant steerable filters. A function is equivariant under some transformation if its output always transforms in a certain way when the input is transformed. In this research, we focus on rotation and scale transformations and study functions which are equivariant under these transformations. In digital histopathology, tissue slices can be captured at arbitrary orientations and magnifications. When conventional CNNs are applied to histopathology image analysis, the generalization performance of models is limited due to two reasons. Firstly, a part of the parameters of filters are trained to fit rotation transformation, thus decreasing the capability of learning other discriminative features. Secondly, fixed size filters trained on images at a given scale fail to generalize to those at different scales. In this research, we aim to encode rotation and scale equivariance properties into 2D convolution to improve neural networks' generalization capacity. Simultaneously, we hope that the computation cost and the GPU memory consumption of the constructed equivariant filters remain in low demand. To achieve this, we propose rotation scale equivariant steerable filters. This matrix multiplication shows how we construct the equivariant filters. Given a list of scale parameters sigma, a series of orientation parameters theta, and the order of partial derivative of Gaussian filters with respect to x and y directions, we calculate a sort of filter bases, which are shown on the left-hand side. Inside of each scale group, filter bases are in the same scale, but are rotated when theta changes. The combination coefficients alpha, which are shown in the middle, are used to linear combine these filter bases to generate a convolution filter. Each column vector is shared between scales and orientations to guarantee the consistency of filter shape. Note that we set sigma values to be some constants for visualization. However, they are allowed to be tuned in disjoint ranges during training. Here is a two-layer example to show the training and the inference procedure of an equivariant network built with RSE-SF filters. In the training phase, the input is convolved with single orientation and multi-scale filters and results in features that correspond to different scales. Then all subsequent layers process these features simultaneously and independently. In the last layer, each pass generates a prediction map y-hat, which is used to calculate the cross-entropy loss, with some over these loss functions and use backpropagation to train the combination coefficients of filters. During inference, for each scale pass, we expand filters from one orientation to n orientations. We can do this expansion as the linear combination coefficient alpha is shared between scales and orientations. And we can expand as many orientations as we can until reaches the memory constraint. At the last layer of the network, we explore some channel squeeze operations to reduce feature dimension and then produce multiple prediction maps for the final selection and ensemble. We evaluate the proposed method on 3 datasets and compare it with other equivariant methods. As shown in the figure, our RSE-SF outperforms others on Craig and GLASS datasets, achieving competitive results on the texture dataset. And it is worth mentioning that the RSE-SF achieved state-of-the-art segmentation performance, but is much smaller and more GPU efficient. Our implementation is available on GitHub. If you have any questions, feel free to drop me an email, and thanks for listening.